Hello everyone, welcome to topic 2.3, structure of ionic solids. In this we will look at the essential knowledge that cations and anions in an ionic crystal are arranged in a systematic periodic 3D array that maximizes the attractive force among cations and anions while minimizing the repulsive forces, and those repulsive forces, remember, would be between cations and cations as well as anions and anions. Specific types of crystal structures, so we aren't going to talk about crystalline lattices and the different types of them, like full front body, face centered, any of those. We won't be talking about those. They are not assessed. You might see them pop up, but it's not going to be on an assessment. Coulomb's law is also going to make another big appearance, so hopefully you haven't gotten sick of that one yet. Ionic solids consist of cations. Oop, I forgot to switch my highlighter. Hopefully you switched it. Ionic solids consist of cations and anions. Discrete ionic molecules do not exist. So you don't have, like, for sodium chloride, you don't have one little sodium atom hanging out with one little chloride atom. Or ion. Ions. We're talking about ions. Instead, you have a repeating array of molecules are held together by strong Coulombic forces. Okay, so we have a repeating pattern of sodium and chloride ions, and these oppositely charged ions are adjacent to one another. The following properties are due to that arrangement. These are non-volatile and have high melting points. The ionic bonds have to be broken to melt that solid, which separates oppositely charged particles. This requires very high temperatures to give the particles enough energy to separate. Ionic solids do not conduct electricity. The charged ions are fixed in one place. When we melt or dissolve them in a solution, the ions are free to move and allow electrical conduction. Okay, so it only happens when they are melted or dissolved. Ions are free to move so they can conduct electricity. Many ionic compounds are soluble in polar solvents like water and insoluble, so they will dissolve in things like water, and they are insoluble in non-polar solvents like benzene, octane. Like gasoline is a non-polar solvent. Don't clean up a salt spill with gasoline. Don't clean up a lot of stuff with gasoline. Bad idea. Just no. Okay. Anyways, relative strength of different ions can be estimated from Coulomb's law. Remember that Coulomb's law states that the attractive force, is proportional to each of the charges and inversely proportional to the distance squared. Therefore, calcium oxide, where calcium and oxygen each have a magnitude of a 2 charge, has a much stronger bond than sodium chloride, where those charges are each 1. This manifests in the melting points of each compound, and you see them there, seeing that calcium oxide is much higher than sodium chloride, due to its much larger ionic charges, so stronger force of attraction, so you need a higher temperature to melt them. Similar reasoning can be used to compare ionic compounds with varying internuclear distances. Because chloride is smaller than bromide, sodium chloride has a higher melting point than sodium bromide, so attractive force would be stronger in sodium chloride, requiring more energy to melt it. And so we see a visual here. And we're ready for our I do. So what is KBr, where we have that lattice energy, has a higher lattice energy than Ki? Well, which one? What's the big difference between these two? Ask yourself that. Well, we see that we have the difference of iodine and bromine. Well, what's different between them? Well, what's the same? They're both in group 7A, so they have 7 valence electrons, and technically their effective nuclear charge is a positive 7. Okay, so they technically both see a positive 7 charge, and for iodine and bromine, well, then what's different? Well, it's not their ionic charge, they're both -1. We keep thinking, well, we see that on the periodic table, bromine is above iodine. So what that means is that iodine has an extra layer of electrons. So iodine, if we're comparing sizes, bromine would be much smaller than iodine, right? And so if we have smaller ions, if we make these our ions, if we have smaller ions, so because bromine is much smaller, even when it's an ion, it's much smaller than the iodide ion. The distance between the potassium ion and the bromide ion is much smaller, and we know from Coulomb's law that that would increase the force of attraction. So the bromide ion is much smaller than the iodide ion. So distance between the charged particles in KBr is smaller. So the attractive force, and thus lattice energy, is higher. Okay? So notice with a lot of these things that are charged, it always comes down to how big is it, and what is its charge? How can we relate those two to the patterns we see? So now we're going to draw a particle diagram of rubidium iodide. Be sure to include relative sizes. Well, you want to look at the periodic table, and when we see this, we also know that rubidium forms a +1 charge and iodine forms the 1-. That since rubidium loses an electron, it should be smaller, and I'm just going to label it with a positive, than the iodide ion, which should be negative. And so since we're drawing a particle diagram, it should alternate the positive and negative charges. Okay, and you should, and that's a really small iodide. They're getting smaller, guys. And so you should alternate those, and you should have an even number of, equal number of pairs, just so you don't have weird random charges. Okay. And so the negative ion should be bigger than the positive ion, but not outrageously so. Okay, because they're still kind of close on the periodic table. So now complete the you-do questions and check your work. Thank you for listening.